In this lesson video, we're going to introduce Unit 8, in which we're going to be talking about right triangles and the topic of trigonometry. But the first thing we're going to do is take a look at day 1 here. And all we're going to do for day 1 is identify what radicals are and work on simplifying those. Okay, so we're going to go ahead and get started with day 1 notes. Make sure you follow along in your note packet, please. The first big part of what we're talking about with simplifying radicals, before we even talk about what a radical is the idea of a perfect square. A perfect square is a number whose square root, and you guys, that's all the word radical really means here. The radical is just a term with a square root symbol. So a number whose square root is considered a positive integer. Okay, positive integers are numbers like 1, 2, 3, 4, 5, 6, just your counting numbers. Okay? So numbers that have a square root that would be a positive integer are just those positive integers squared. So those are numbers like 1, 4, 9, 16, 25, 36, so on and so forth, okay? And we get these numbers by taking those positive integers and squaring them, okay? 1 squared equals 1. 2 squared equals 4. 3 squared equals 9. 4 squared equals 16. 5 squared equals 25. 6 squared equals 36, and so on and so forth. And to find these perfect squares, you just keep squaring the next integer. So if we were to do 7 squared, that would be 49. So 49 is your perfect square. Okay, perfect squares is this row of numbers. The numbers that we're squaring to get those would be their square roots. For example, the square root of 25 equals the integer 5. Okay? And so when we simplify radicals, the very first thing you always check for is the number on this list of perfect squares? Okay, so we've got our list of perfect squares. I'm going to condense this and go ahead and finish out our list. Let's try this. Hold on. Just move things out of the way a little bit. So the next perfect squares are found doing this. 8 squared, 9 squared, 10 squared. And for right now, that's as high as I'm going to make you go. You could do 11 squared. Some people memorize on up to 12 squared or even 20 squared. But for now, we're just going to write these next ones down. 8 squared is 64, 9 squared is 81, and 10 squared is 100. So there are your first 10 perfect squares. Now, I do want you to be careful. This first one, 1 squared equals 1. That number 1 is a perfect square, but we won't really use that to simplify anything because it doesn't change the number. When you divide or multiply by 1, it doesn't change any other numbers, and so that doesn't help us as much. And so we won't use that one as often. So when we're simplifying these radical terms, these are all examples of radicals. Square root of 64, square root of 20, 3 square root of 50. Those are all examples of radical terms or radical expressions. So when we are simplifying them, the first thing you always do is check to see if that number under that radical, underneath that square root, is actually a perfect square already. So in this example, 64 is a perfect square. The square root of 64 is just 8. 8 squared gives you 64. So that one's done. Okay, you check and see if it is, and then you can do that. And you have square root buttons on your calculator that you can use. Okay, when bringing up your calculator, to find the square root button, that is right here. Okay, it's right above the x squared key on most calculators. If you're working with a different calculator, I can show you where to find that in class. But to do the square root of that example 64, I would type my second button, then my x squared to bring up the square root, put in your 64, and it does the square root for you. Now, if you try and do the square root of a number that is not a perfect square, like our next one, 20 is not a perfect square. It's not on my list of perfect squares. If I do the square root of 20 and hit enter, I get a decimal value. Well, sometimes we get to write our answers that way, but a lot of times we don't want to do that. We want to write answers in math sometimes as exact answers. This decimal, no matter how long I write it, is not going to be exact. These decimals would keep on going forever and they would never repeat. And so they're not ever going to be an exact decimal answer for these kinds of square roots. So what we have to do is figure out a way to write an exact answer so that we're not using a rounded answer in any other calculations or giving answers. So to do this, we use the process of doing the simplest radical form, simplifying the radical. So the first thing we do is we check and see if it is a perfect square. 20 is not a perfect square. It's not on that list of perfect squares. Okay, it would fall right here between 16 and 25. Okay, so it's not there. So what we have to do is determine if there are any other perfect squares that can be divided into that radical without there being a decimal. So what that means is we're looking for factors of 20, things that would multiply to equal 20. Well, that involves making something kind of like a factor tree. There's things that can multiply to equal 20, like 1 and 20. But again, while 1 is on that list, that doesn't help me because it doesn't change the number 20. You could divide 20 into 2 and 10, but neither of those numbers are on this perfect square list. You can't divide by 3, but you can divide by 4. 20 divided by 4 is 5. Now, 4 is one of these perfect squares. 4 is on the list, right there. So that means I can split my 20 into the square root of 4 times 5, because 4 times 5 equals 20. I'm just rewriting it a different way. When we have the square root of two numbers multiplied together, you can take the square root of each of those separately, like this. This is just an exponent rule, actually. Okay? This is just something we can do. We can split that into the square root of 4 times the square root of 5. Now, the square root of 4 can be simplified. We can take the square root of that perfect square in our head or our calculator without getting a decimal. The square root of 4 is 2. And then I have to leave the 5 because it is not a perfect square. So my final answer for simplifying the square root of 20, I can get rid of that multiplication sign and just squish those together and call it 2 square root of 5. Or we would read that out loud, 2 root 5. That's how you would read that. But this is your answer. Now, some of you might be looking at that and thinking, oh, well, that's not simplifying really. It's simplifying because we have simplified the individual numbers. The numbers themselves are smaller, but we can only go as far as we're allowed to without getting decimal answers. Okay? Let's try one more. Now, this number is a little different. There's already a number outside of that radical. The 3 here is not part of the radical, so the 3 just hangs out in front until there's another number like it that can be multiplied with it. Now, and when I say another number like it, I mean another number that is not under a radical symbol, another number that is not a radical. So really, we're looking at the square root of 50 part first. Okay, that's the part we're going to split. And again, we're trying to decide what numbers off of this list of perfect squares up here, what numbers off that list of perfect squares can be divided into 50, or can we divide 50 by? But we want the biggest one. You don't have to always find the biggest one first, but it definitely saves you a lot of time. So I want the biggest number off of that list of perfect squares that you can divide 50 by. Well, actually, the only number you can divide by is this 25. So I can split the square root of 50. Remember, I can do these two as separate square roots. Is the square root of 25 times, do not write 25 in the second one. We're not subtracting 25, we're dividing by 25. When I get to my other number, I'm doing 50 divided by 25, which is 2. Okay? So I can start to simplify this a little bit more because the square root of 25 is just 5. But remember, we have this 3 hanging out in front, and it's multiplied. There's a multiply sign that we don't bother writing in there because when you have two numbers stuck together like that, you can imply that there's a multiplication. So we're really doing 3 times the square root of 50, so it's 3 times the square root of 25 in the front here. So it's 3 times 5 at the front. 3 times 5 we can further simplify to be 15. The square root of 2 stays at the end of my answer. So that is your answer, and we would read that 15 root 2. Okay? So that's simplifying radicals. Well, that is also involved in doing other operations with radicals, like multiplying radicals, okay? If we're multiplying radicals by the radicals and constants, if we're multiplying the radicals by the radicals and constants by the constants, do not mix them, okay? And sometimes you'll have numbers to mix, sometimes you won't, but we want to always put things together that are alike. The numbers that are under a square root can go together. The numbers that are not under a square root can go together, okay? But we have to keep those two things separate. And then also make sure your very final answer is always in simplest form by following these previous steps we just did in the previous example, okay? So let's try this. On example 2, we have a square root of 5 times a square root of 2. Well, remember, that means I can put them both under the same square root as 5 times 2. 5 times 2 is just 10. Now, 10 is not one of my perfect squares. Excuse me. From your list at the top, 10 is not one of my perfect squares. Since 10 is not one of the perfect squares, I need to look and see if it can be divided by any perfect squares. But the only things you can divide 10 by are 1, 2, 5, and 10. And none of those are perfect squares, so root 10, or the square root of 10, is your final answer. Okay? Let's try part B. We can put those underneath the same radical together, 6 times 3. When I do the square root of that all together, I can multiply 6 times 3 and get 18. So I have the square root of 18. But again, I want to check first and make sure it's not already on my list of perfect squares. 18 is not. It's between 16 and 25. But I also want to see if it can be divided by any of those numbers off that list of perfect squares. You should recognize that 18 can be divided by 9. 18 divided by 9 is 2. So I can split the square root of 18 into the square root of 9 times the square root of 2. Square root of 9 times the square root of 2. The square root of 9 is a perfect square. So that means I can get the square root of 9 is 3. And then I leave my root 2 after that, and so my answer is 3 radical 2, or 3 root 2. Okay, part C. This time, we do have two numbers that are alike, but they're outside of the radicals. 5 and the 2 are not the same, or they are the same kind of number. They are not under a square root, so they can come together as 5 times 2 out front, and then that leaves the square root of 27 over here by itself. So that's going to hang out for a minute. 5 times 2 is just 10, so I have a 10 in front of my square root terms, and then I have my square root of 27, but now I want to see if that square root of 27 can be simplified. 27 is not a perfect square, it's just after 25. But it can be divided by perfect squares. 27 can divide by 9 and give you 3. 9 and 3 are my two numbers I can use then, because 9 is a perfect square. So I'm going to leave my 10 out front and rewrite the square root of 27 as square root of 9 times the square root of 3. The square root of 9 is the part we can simplify, since 9 is a perfect square. Out front I'll have a 10 still, but now it's times 3, and then your root 3. And so 10 times 3 is 30. And then I keep my radical 3, or my root 3. And so my answer is 30 root 3. Okay? So that's multiplying radical expressions. We can also, if you go to the next page, divide radical expressions. Now at the top of this page, so I don't have to keep flipping back and forth, I'm going to go ahead and write the list of perfect squares again. I'm going to not really include the number 1. I'm going to start with the next one. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. So there's my list of perfect squares I'm going to be using. So when we're dividing, we can simplify the constants and divide the radicals. So we can divide the parts that are considered constants, the non-radical terms, and we can divide the radicals. We can do those separately. If the radicals can't be divided, we'll have to do something called rationalizing the denominator. So we'll do some examples without having to do that first, then we'll come back and show you how to do that. And then always make sure your answer is in the simplest radical form, using the steps we've talked about already. Okay, so on the first one, I have the square root of 14 over the square root of 2. I need you to remember that means the square root of 14 divided by the square root of 2. Remember that those fractions mean division. So I can actually divide those because they're both radicals. So I can actually rewrite that as the square root of 14 all divided by 2 like that. 14 divided by 2, I can do that. That's 7. So this is just the square root of 7. And 7 is not a perfect square, nor can it be divided by any perfect squares. 7 is a prime number. It can only be divided by 1 in itself. So this is your final answer, the square root of 7. For part B, now we have two portions to consider. We have the non-radical terms, 2 over 4, and the radical terms, root 6 over root 3. And so we can think of those as separate pieces. When I do when I do 2 over 4, I can do some canceling. Okay, they both divide by 2. On the top number, 2 divided by 2 is 1. On the bottom number, 4 divided by 2 is 2. So I still have that part. Okay, but my radical terms now, I can think of as just the square root of 6 divided by 3. 6 divided by 3 is just 2. So I have my 1/2 here, but then I also have my root 2. Now that 2 is no longer a fraction. Okay, 6 divided by 3 is just 2. That's no longer a fraction. So that number will always go on the top of this fraction. So I'm going to rewrite that as 1 times the square root of 2. But when you multiply something by 1, you get whatever that thing is. So the real answer is just root 2 over 2. Because I can't simplify those. One is a radical, one is not. And I don't have a square root term in the bottom of my fraction anymore, so this can be my final answer. Okay? Now we're going to talk about what it means to rationalize the denominator. And the reason we have to rationalize denominators sometimes... Oh, I'm sorry, I forgot. There's an example. Let's go back. Got a little ahead of myself. So again, we're going to start simplifying these fractions as far as we can. We have our 3 over 6. Okay, that part can be simplified into 1 over 2 because 3 divides by 3, 6 divides by 3. We get 1/2. But then we just have one radical expression of 12 divided by 3. 12 divided by 3 is 4. This term is going to go on the top again. Okay. Now, the square root of 4 times 1 is just the square root of 4, and that's all over 3. Now, this would seem like our final answer, except the square root of 4 shows us 4 is a perfect square. 4 has a perfect square root. It has an exact square root, an integer answer. The square root of 4 is just 2, so I'm going to simplify that. And the bottom number of my fraction stays 3. All right, now we can go on. Now we can go on to the process of rationalizing a denominator. And this is when there ends up being the square root on the bottom of a fraction that can't be simplified any other way. Okay, we're going to use to simplify when there's a radical in the denominator. That's the bottom of the fraction. And the way we do that is to multiply the numerator and denominator by that radical term. Now, this can't be simplified. 5 and 2 can't divide, so there's really no way to put those together or simplify them. So the rationalizing gets to happen right away. To do this, we're going to multiply this entire fraction by something that equals 1. Okay, this new fraction equals 1. That means it has to be the same thing on the top and bottom of the fraction. That's why we're multiplying the numerator and denominator by the same thing. The only way to get rid of the square root term is to multiply it by an identical square root by itself. So we're going to multiply by the square root of 2 on the bottom and the square root of 2 on top, because root 2 over root 2 does equal 1. Okay, and what this does, it rationalizes that bottom number, because these numbers that can't be simplified, these square root terms that can't be simplified, are considered irrational numbers. They're numbers that can't be written as a fraction of integer values. So they have these decimals that go on forever. Well, I'm going to rationalize that. I'm going to turn the bottom of the fraction into a rational number, a number that is not a never-ending, never-repeating decimal. So the root 2 times root 2, remember, when I group two radicals together, root 2 times root 2 is root 4, right? But the square root of 4, I already know, is just 2. So the new bottom of my fraction is just the number 2. So you should notice as you do this, a pattern. Root 2 times root 2 equals 2. Okay, over here on the side, I'm going to make a little note to you. Root 2 times root 2 equals 2. So root 3 times root 3 would equal just 3. And root 4 times root 4 would equal just 4. And root 5 times root 5 would equal just 5. So the pattern continues that the square root of some number x times itself, the square root of some number x, equals just that number x. Okay, so that is what we're using to rationalize that denominator. But on the top, root 5 times root 2, those are two different numbers. So I can group those together as the square root of 10, because 5 times 2 is 10. And you will remember from the previous example on the front page that the square root of 10 cannot be simplified. So root 10 over 2 is your answer. Okay? Let's try another few of these where we have to rationalize this denominator. On part A, we have root 3 on the bottom of this fraction, so we're going to multiply top and bottom by that same root 3, because that does not change the value of the fraction. Okay, on the bottom of that fraction, root 3 times root 3 is just 3. On the top of the fraction, 7 times 3 is 21. Now, 21 is only equal to 7 times 3. You can only divide 21 by 7 and 3, or 1 and 21. Now, none of those numbers are perfect squares, so this cannot be reduced or simplified, and that is your answer. Let's try another one on part B here. The bottom of the fraction is root 2, 5 over root 2. Nothing will simplify or change there. So I can multiply the bottom by root 2 and the top by root 2. On the top, though, those cannot be combined. I have to leave it as 5 root 2. But on the bottom, root 2 times root 2 is just 2. And then I do need to look at these two numbers, the 5 and the 2. Those cannot be simplified. Okay, I can't do 5 over 2 and get anything other than a decimal. So I'm going to leave that as my final answer. 5 root 2 over 2 is the simplified answer of that. All right, one more example. 12 and root 3 cannot be combined. This 12 is not a radical, and 3 is under a radical. But you need to notice the pattern. When there's a radical on the bottom of the fraction, we're going to multiply by that radical on top and bottom. On the top, those cannot be combined, so it has to stay 12 root 3. On the bottom, root 3 times root 3 is just 3. But this time, the 12 and the 3 do have a common factor, and they can be simplified. 12 does divide by 3 evenly. 12 divided by 3 is 4, and I still have my root 3 after that. On the bottom of that fraction, when I cancel that, 12 divided by 3 is 4, 3 divided by 3 is 1. When the bottom of your fraction is 1, you don't have to write that. Okay, I don't have to write the over 1 part of that because it's unnecessary. So that is my answer, 4 square root of 3. So as we go through this lesson, this list of perfect squares is going to be very, very important. Okay, and actually as you start your assignment, that's one of the first things you have to do is to make that list. Okay, So I've given you a lot of this to start with. But this finishes our lesson notes on day 1, simplifying radicals.